Before we jump into the topic of locating vertical and horizontal asymptotes, we will review something that you already know. In section 4.4.2, we will discuss the domain of a rational function. The domain of a rational function is the set of all x values for which a function is defined. What that means is I have to exclude all values of x from the domain that cause the denominator to be 0. Remember, in the definition of a rational function, it is defined only where the denominator is not 0. If I use my calculator to try to divide a number by 0, the calculator tells me it is an error. This is an undefined operation. This is what we are avoiding when we exclude values from the domain that cause a 0 in the denominator. In example 1, we're going to state the domain of rational functions using interval notation. The first function is f of x equals -3 divided by x minus 4. The numerator can have any value between -∞ infinity. In this case, it's a static value of -3. But the denominator cannot be 0. So we're going to take our denominator out and we're going to set it not equal to 0. This is what we're trying to restrict, so we can see x cannot be equal to 4. If x is equal to 4 and I plug it in here, I would get that 0 in the denominator. So we say that 4 is the restricted value of the domain. This is our restricted value. That means x can have any possible value between -∞ to infinity, but not 4. So if I think about my x-axis from -∞ to infinity, I want to use all possible values except 4. So I'm going to think about removing that single point, like plucking a hole into our x-axis. And notice that divides our axis into two different pieces. The domain then can be expressed in interval notation from left to right. The leftmost value on that number line is -∞, and we're going to go right up next to 4 but not include it, and so we're going to illustrate that with a parenthesis. Remember, parentheses indicate that we are not including the endpoint as part of the domain. So there's the left side. On the right side of the graph, we're going to read that from 4 to the rightmost value of infinity. As a reminder, this symbol U means union. So everything in the first interval together with everything in the second interval represents the domain of that rational function. Now, let me show you how the domain is related to the graph. If we go to our graphing calculator, let me clear this out, and we graph our rational function, -3 divided by, now I'm going to be really careful how I plug this in. I got to make sure and get that operation in the denominator in a set of parentheses. Okay, so this is the correct way to plug in our rational function. Notice when we graph this rational function, it results in two pieces, right? Remember, our domain had two intervals and our graph has two pieces. That's no accident. The left interval of our domain, -∞ to -4, that's describing the x values used on the left branch of our graph. The right interval in our domain, 4 to infinity, that's describing the values used on the right branch of our graph. So the domain indicates how many branches our graph is going to have. Let's look at example B. f of x equals 3x plus 1 divided by x squared plus 3x plus 2. Remember, the numerator is free to take on any value, including 0. It's the denominator that we want to make sure is not equal to 0. So notice if I find the zeros of the denominator here, I've basically got a quadratic equation. We can solve this by quadratic formula or by factoring. Notice this one factors very simply, and we get 2 zeros here, or in this case we're calling them restricted values. So x can have any possible value except -2 and -1. So I'm going to use the tool of the number line to convert this into interval notation. So I'm going to consider the location of -2 and -1 on the number line, and I'm going to imagine removing those 2 points, leaving holes behind. Then we can read the domain from left to right. The leftmost value is -infinity, and we're going to come up right next to -2 but not include it. Remember, that's what the parenthesis is for. Then we're going to look at values in between, so from -2 to -1, and then values on the right side, which would be -1 to infinity. Now, if I relate this to the graph, I would anticipate 3 different branches to the graph. So taking a quick peek at the graph, I'm going to go to y equals. Now really practice putting this in your calculator so that you'll know the correct syntax. If you have an operation in your numerator or denominator, make sure you enclose it in a set of parentheses. So I'm going to put the numerator in parentheses and the denominator. And we'll take a peek at the output, looking at the graph. We are anticipating 3 branches because our domain had 3 branches. And it looks like we have 2. Let's zoom out a little bit. So I'm going to press my zoom button, number 3, and then I'm going to press enter. And we are going to look for the 3 different branches. Okay, that's a little better, but not much. It's very subtle there. Let's play with our window manually. If I press my window button, the x values are from -40 to 40. I'm going to do half of that, -20 to 20. And I don't think the graph is very tall, so I'm going to go back to -10 to 10 for the y values. You can experiment with that until you have a satisfactory output for your graph. So there's the first branch, there's the second branch. I didn't quite make it far enough. Let's try x max to be 40. Again, we're looking for 3 branches because we had 3 branches in our domain. Three, 2, 1. Example B, f of x equals 3x plus 1 over x squared plus 3x plus 2. Remember, the numerator can take on any value that it wants, but the denominator has to be non-zero. So let's find the zeros of the denominator. Notice this is an ordinary quadratic equation that we could solve by factoring. This one easily factors as x plus 2 times x plus 1. So we have 2 restricted values. X cannot be equal to -2, and x cannot be equal to -1. I'm going to use the tool of the number line to visualize the domain in interval notation. So our restricted values are -2 and -1, and I'm going to imagine this as removing those single points from the number line. Then I can see that the number line is broken up into 3 intervals. So I'm going to read the domain from left to right. The leftmost value here is -infinity up to -2. Then we're going to look at the values between but not including -2 and -1, and then values on the right side of -1. So that would be from -1 to infinity. Our domain has 3 intervals, so we could anticipate 3 branches for the graph. Now, if you'll take a peek at the graph, notice whenever I plugged it in for y equals, I enclosed both the numerator and the denominator in a set of parentheses. Now, looking at the graph in the standard viewing window, it was difficult to see all three of the branches. So by experimenting with trial and error, I set my window manually. So I typed my window button, set the x minimum to -5 and the x maximum to 5, the y minimum at -20, and the y maximum at 20. Again, I found that spending a little time by trial and error, searching for the best window to view those three branches. Then you can definitely see the three branches. The leftmost branch here has values from x values from -infinity to -2. In between here, between -2 and -1. And finally, the rightmost branch has x values from -1 to infinity. Let's consider example C. The function is y equals 4 over x squared minus 25. The numerator can have any value. In this case, it's always going to be 4, but we want to make sure our denominator is not equal to 0. Now, you could think about this one two ways. You could factor this as the difference of two squares, x plus 5 and x minus 5, and you could see your two restricted values are then -5 and 5. Or if you think about it differently, you could solve it with, you could solve it with your square root property. So add 25 to both sides, take the positive and negative square root of both sides. Either way, your restricted values are going to be -5 and 5. So when we convert this into interval notation, let's use the tool of the number line. If you're comfortable imagining it without the number line, that is great. This is just a tool to help us visualize what's going on. Our domain would be in three pieces: -infinity to -5, between -5 and 5, and from 5 to infinity. So if we graph this function, we would anticipate 3 branches to the graph. Our last example is a little bit different. Notice on example C, we had the difference of two squares in the denominator, whereas on this example, we have the sum of two squares in the denominator. Now, the sum of two squares does not factor. So if I say this denominator cannot be equal to 0, and I attempt to solve it by the square root property, notice I'm going to end up taking the square root of a negative number. Don't forget your plus or minus. So in this case, we would get x can't be equal to plus or minus 5i. Well, those are imaginary roots to the denominator. Those will not appear on the number line. So there's no restricted values for this function. No restricted values. Thus, our domain then is -infinity to infinity. Another way to think about it, no matter what value I plug in for x, when I square it, it's going to be positive. And then when I add 25 to it, it's still a positive number. It's never going to be equal to 0. Since the denominator is never equal to 0, the domain is -infinity to infinity. Let's take a quick peek at the graph. Remember, when you type this in, you need to get your denominator in a set of parentheses. And I'm going to go back to my standard viewing window by typing zoom 6. And the first graph is not that exciting. I notice that it's really close to the y-axis there. So again, I'm going to adjust my window manually. I think the spread from -10 to 10 is good for x. But I'm going to decrease my y values, the y minimum at -1, the y maximum at 1, and then I'll be able to see a little bit of the curvature of the graph. Notice there's no jumps, there's no asymptotes, so the domain is in fact -infinity to infinity. Now, if you can find the domain of a rational function, you are well on your way to finding vertical asymptotes, and that's what we'll talk about in the next video.